So what we've done so far, we've rewrote Maxwell's equations in a neater form. And we saw that in order to do that, we had to introduce this object eta, which is a strange matrix with minus ones and pluses ones in it. And roughly speaking, you could say we needed it because some of the Maxwell equations had lowered indices on the F mu nu, and some had raised indices. And we used this guy to raise and lower indices. And that allows us to introduce some minus signs. Okay? So it sounds like a little trick, but it is. But it's a very fundamental one. And once we'd introduced it, we required that all the laws of physics and our description of physical phenomena be invariant under transformations which preserve eta. Right? So just as we are familiar with the fact that rotations leave lengths invariant, there are transformations that leave, and lengths are defined by the sum of the squares of the components, Pythagoras rule. And that implicitly uses a delta ij in Cartesian coordinates. The sum of the squares can be written as the sum with a delta. So x squared is xi xj delta ij. And so when we went to space-time and we had this funny minus sign, we replaced this by x squared, which is eta mu nu x nu, or more generally by u dot v, where these are both four vectors, u nu. And it's plausible that since the laws of physics are invariant under the symmetries, the Lorentz transformations, the Poincare transformations, we should only ever really, whenever we describe some physical process, we always have to be sure we're talking about things which are invariant under those operations. So this eta is the analog of delta, but in space-time. And I've already mentioned the Poincare group. And this Poincare group is, I'm now going to define and derive it as the group of coordinate transformations which leaves this eta invariant. Okay, so we have, so this is the group of, and it will turn out to be twice differentiable coordinate transformations and what I mean by a coordinate transformation is changing coordinates from x to x prime, which is a function of x. So each of the four coordinates in x prime are functions of the four coordinates x. When I say twice differentiable, I require that I need to be able to differentiate these functions two times, and that's meaningful. Which leave eta mu nu unchanged. Okay, so if I think about writing down Maxwell's equations, the one thing I want is that the Maxwell equations should be valid in all coordinate systems, right? I mean, because I think all of these coordinate systems are equally legitimate. All of the ones related by rotations or boosts, they're equally good coordinate systems. So if I write down some physical laws, they better be valid in all those coordinate systems. Now we know how the F mu nu transforms. Right? It transforms as a tensor. Let's do it with upstairs indices. Lambda mu alpha, lambda nu beta, f alpha beta, etc. Right? So the rule is all the quantities I'm going to put in the equations transform like tensors. That's a good start. And well, that's sufficient to ensure that the equations will hold in all of these coordinate systems. But I always have this eta, right? And eta should transform just like a tensor. Okay, but I want this eta to equal the old eta. So I want to write down the equations and them to be valid in any coordinate system. Eta isn't really anything physical. So we require. And this led us to Lorentz transformations. Okay, so what I want to show is the most general coordinate transformation, which is second differentiable and leaves eta unchanged in this sense, will actually be the Poincare group. So far here, we just did linear coordinate transformations, right? The Lorentz transformations, but now I'm going to generalize that. And so we'll see that the Poincare group, including the Lorentz group and translations, is a very special subset of general coordinate transformations. And it's going to be very useful to think about general coordinate transformations because as soon as we start to do that, we'll realize there's a new force, which is gravity. Okay, so let us consider a coordinate transformation. Okay, satisfying eta gamma delta equals eta alpha beta dx prime alpha dx prime beta dx gamma dx delta. Okay, so what I'm using here is the fact that the way a tensor will transform under this general coordinate transformation involves these Jacobian matrices. These are the generalization of the lambdas. And that's fairly obvious because we know that an infinitesimal 4-vector in the obviously transform with an upstairs index should transform like this. Right, so that's a 4-vector, and dx is equal to dx prime times. So I get this equation just by differentiating this. When I take d of this, obviously it's the partial derivative of the x prime with respect to the arguments times the dx. And likewise, I have d by dx prime alpha, a derivative, transforms with the inverse matrix. Okay, so since a small displacement of coordinates transforms with the Jacobian and the derivative transforms, partial derivative transforms with the inverse Jacobian, that already tells us how quantities with any number of indices should transform. I just use the appropriate number of these Jacobian matrices. So that's the generalization of a Lorentz transformation to an arbitrary coordinate transformation. And what I want for my eta, if I want my Maxwell's equations to be valid in any coordinate system, I want the eta prime to equals eta. Right? I want eta, the transformation of eta, to leave eta unchanged. So the claim is that the most general such coordinate transformation is a Poincare, is an element of the Poincare group. namely x prime mu is lambda mu nu x nu plus a nu with lambda mu nu lambda gamma alpha eta mu gamma equals eta nu alpha. In fact, these are the way I've written it. These are down. Let me do it the other way around. Should have been lambda twiddles. Okay, so that's the claim. So let's let's prove it. And this is a kind of manipulation which Riemann invented. And it'll be a sort of model of several calculations we'll do in the future. So just stare at this equation. The right-hand side is a function of x, because x prime is a function of x. We don't know what kind of function yet. The left-hand side is independent of x, so obviously let's differentiate it with respect to x, and we'll get some equation for x prime of x. So differentiate this. So d by dx epsilon of this equation, and it gives us 0 equals, and then eta alpha beta d2 x prime alpha dx gamma dx epsilon dx prime beta dx delta plus eta alpha beta. I just have to differentiate the first term or the second term. Okay, so I just took d by d epsilon of this term, d by dx epsilon of this term, and then of this term, and these are the two terms. So that's 0. Now, what do I want to do? Well, I want to get a single equation for this d2 x prime dx dx. I want one equation, which I can then solve. And this is rather complicated. So now this is Riemann's trick. You add this equation with gamma exchanged to epsilon. You see this first term is symmetrical under gamma to epsilon. So if I switch gamma and epsilon and add, I'm going to get the same term again here. But I don't like this term. This term is symmetric under delta goes to epsilon, and I want to get rid of it. So I should subtract the equation with delta goes to epsilon. So I subtract the equation with delta goes to epsilon. That at least is going to cancel this term. Okay, so that's the trick. You add an equation with the thing you want, reversed indices, and you subtract with the thing you want, with things you want to get rid of with reversed indices. Now we're going to get 6 terms, so let me write them out. So we'll put a plus here. Eta alpha beta d2 x prime alpha dx epsilon dx gamma dx prime beta dx delta plus eta alpha beta d2x prime alpha dx epsilon d2 x prime beta dx delta dx gamma. All right, so that's good because this is the same term coming in again. I've got this nasty term. But something very nice will happen when we subtract the term with delta going to epsilon. That'll get rid of this guy, that's obvious. Right, d2x prime alpha dx gamma. So I'm going to subtract this, d2x prime beta dx epsilon dx delta. So immediately these will cancel. And over here, I've got to take the first line, but with delta going to epsilon, so I get eta alpha beta d2x prime alpha x gamma dx delta dx prime beta dx epsilon. Okay, so obviously what's happened is this guy has doubled because these are just the same term. Can you notice something nice has happened? Except I've written a 2, which shouldn't be a 2. What's happened with the third, this term and this term? What do those two terms do? Look pretty much the same, right? How do I make sure this term is the same as that term? It's not quite the same. X prime beta, X prime alpha, X prime alpha, X prime beta. So what should I do?
Relabel the indices.
Relabel the indices, exactly. So we can just relabel this beta alpha, and this beta and this alpha. It doesn't change anything. And eta is symmetric, right? So this is equal to eta alpha beta. And now they exactly cancel. Right? So this one cancels with that. Okay, so by doing this, yeah.
Couldn't we have just done this last trick where you recognize that eta is symmetric right
Mm-hmm.
at the very start without adding and subtracting these things?
No.
No, why is this?
So this is the equation we had, right?
Yeah, why can't the second term just be set equal to the first term using that same trick?
Okay, good question. Look at the free indices in this equation. So the alpha and the betas are contracted. The free indices are gamma epsilon
Right?
in a second derivative. Here it's delta epsilon.
Right?
It's not the same term at all. Totally different term. There's no way to combine this term with that term. I mean, the indices on the second derivative are different in the two terms, and the first derivative likewise, different
right,
index.
Sorry. See, they're switched. Yeah.
Yeah, so this is dx delta. Oh, I see what you mean. Right. Here the first derivative is second, and here it's first. So you can always shuffle them around because I just put it here.
Gammas.
Right. Okay. So the first equation looked pretty hopeless, but when you do this Riemann's trick, now you just have one equation. You see here, the second derivative indices are the same, and here the first derivative index is the same. So these really are identical. So that means that eta alpha beta d2x prime alpha dx gamma dx epsilon dx prime beta dx delta equals 0. That's a nice equation. What do you suggest I do with that equation? You see, I've still got this kind of unpleasant factor here, this Jacobian matrix. Can I get rid of it? How do I get rid of a Jacobian matrix? Imagine I've got some matrix equation, mn equals 0, and I want to solve for m. I want to get rid of the n. So how do I get rid of it? Inverse, yeah? So I just multiply by n inverse and get rid of it. So I have the inverse of the Jacobian matrix, because I told you the coordinate transformations have to be 1 to 1. That implies that this matrix has to be invertible. And so we multiply by dx prime, right, with the right indices. So dx delta, to contract that guy, delta is the free index, dx prime mu, let's say. Right? And then we are going to use dx prime beta, dx delta, dx delta, dx prime mu. What does this mean? Well, this is just the partial derivative of x prime beta with respect to x prime mu, using the chain rule, right? So this is equal to dx prime beta dx prime mu, because x prime is a function of x. So when I differentiate it, I differentiate x prime with respect to x, and then I differentiate x with respect to x prime. And this is delta. If I differentiate a coordinate with respect to itself, I get 1. If I differentiate it with respect to some other coordinate, I get 0. So this is delta. Okay, so we can just get rid of that term by multiplying with the inverse Jacobian. Let me just raise these. Okay, and so when I do that, I'm going to change this into a delta mu, delta beta mu, and the delta beta mu will change this index to a mu, so I get eta alpha mu d2x prime alpha dx gamma dx epsilon. Right, and I have this free index mu. Well, I can get rid of the eta because eta times eta inverse is 1. So now I just multiply it by eta inverse, eta mu nu, let's say. And then this will give delta alpha mu, and I get d2x prime nu over d gamma dx epsilon equals 0. Okay, so the only coordinate transformations leaving eta invariant are ones satisfying this equation. Now this equation is quite easy to solve, because what you have is the partial derivative, d by dx of something, is 0. Right? All 4 partial derivatives are 0. So d by dt, d by dx, d by dy, d by dz, they're all 0. So this implies that the thing the derivative acts on, which is dx prime nu dx epsilon, equals what? If the derivative of something is 0, something has to be a constant. It's the only solution. So that's lambda nu epsilon. Right? Constant. Some matrix lambda nu epsilon. And then because we have to have this equation, we can immediately see that matrix must be the Lorentz transformation, right? Because we can plug the solution back in here, and we can see that lambda, lambda, eta must be eta. Okay, so this is Lorentz. We still haven't solved for the x prime, but this is saying that the derivative of x prime with respect to x is a constant. What's the general solution of this equation? That x prime nu of x must be equal to lambda nu epsilon. So if the derivative is a constant, I have to have that, right? It's a linear, the derivative of a linear function is a constant. And then there's an integration constant, plus a nu. And so that's Poincare. Okay, so it's not hard to prove that the most general coordinate system, which would leave eta invariant and therefore leave the Maxwell's equations invariant, is the Poincare group, and there's nothing else. Any questions? Yes?
Did you just relabel alpha to nu?
Yes. Sorry, here?
Yeah. Or
Well, no, actually, I had this eta matrix, and it's contracted with the x prime. So I want to get rid of it. So what I do is multiply by its inverse, right? Eta mu nu, I just multiply it with eta mu nu and use that eta mu nu times eta alpha mu is delta nu mu. And then this delta mu nu, well, delta nu alpha, right? This delta nu alpha will change this index to a nu, which is what I got here. Okay, you'll get used to this. When you do it enough times, it'll become second nature. So the trick is to write all these equations with indices and then somehow mentally be blind to the particular labels of the indices. You have to do. You have to sort of envisage all the symmetries and everything without taking any individual index too seriously. We see now that eta and the Lorentz group and the Poincare group are tied together very strongly, right? Eta and Poincare come together. And Poincare, group of translations and Lorentz transformations, is the group of symmetries of Maxwell's equations. And that's the foundation of relativity, special relativity. Now, the whole idea of general relativity is to say, let's do something more general, right? Let's try and get rid of eta. So this is special relativity. General relativity is saying, well, maybe eta is a little bit too special. It's a bit of an ugly thing. It's sitting in the Maxwell equations. It's this funny constant matrix. Why should we allow that to be fundamental? Let's allow eta to be something more general. G. Okay. So let's just replace eta by a symmetric 4x4 matrix, which can be a function of x. That's the whole idea of general relativity. And then what's the meaning of this matrix? Well, as I said, what we do in special relativity is we use eta to calculate invariant quantities. For example, a proper time, right? We drew a particle trajectory in space-time, and we said, what is the Lorentz invariant distance along the particle's trajectory? And the way we calculated it is we worked out eta mu nu dx mu dx nu. That's Lorentz invariant. It happens to be negative for a time-like path, so we did this, and then we took the square root, and that was the proper time. And all observers are going to agree on that quantity, right? For any 2 points on the particle world line is invariant. So clearly, if we're going to replace eta with a more general thing, G, we're going to use this G now to calculate invariant quantities. So this is going to go over to root minus G mu nu of x dx mu dx nu. Okay, and that will turn out to be the way to introduce gravity into the motion of a particle. So all you do is just take the eta and the formulae we wrote down before and replace it with G mu nu of x, and this G mu nu of x describes the effect of gravity. Okay, that was Einstein's insight. That gravity is this quantity, and this quantity is described by this quantity, and this quantity describes the geometry. It tells you how to calculate lengths, so it tells you how to calculate distances, angles. You calculate angles by taking two vectors, and the dot product between them is invariant, and so on. So this tells you how to define coordinate, invariant, lengths, and angles, and some other stuff, which we'll see shortly. Okay, so we want to go from eta to g. Well, how should g to g transform under coordinate transformations? And the idea is just to generalize this. The idea is that g mu nu of x, whatever this matrix function of x I have, if I change coordinates, if x goes to x prime of x, then g mu nu should go to g mu nu prime of x prime, which is equal to dx dx prime, just like the eta. And this idea that the g is measuring the geometry should already give you the picture that we're going to imagine that Minkowski space, whose metric, whose the quantity used to measure distances and angles in Minkowski space is the eta matrix. We're going to imagine that Minkowski space is flat, perfectly flat space, but space-time, but something with a g is curved. That's what we're doing. We're going to be describing a curved geometry. So this is curved geometry. And this is, eta is describing a flat geometry. Okay, so let's just run with this idea that we introduce some g of x. We require the theory to be invariant under these more general transformations. Okay, so this is an arbitrary one-to-one mapping. And that requires that dx prime dx, these Jacobian matrices, are invertible. So that dx prime, we can write this equation down. Etc. Because these equations didn't require the coordinate transformations to be linear. Those equations are valid for any coordinate transformation. So we do require that these coordinate transformations are good in the sense there's a one-to-one correspondence. Every x corresponds to one x prime and vice versa. And that, with various assumptions of smoothness, which I won't get into, is enough to ensure that these Jacobian matrices exist and that they're invertible. And in general, we're going to need twice differentiable functions. We're going to need these coordinate, maybe even 3 times. But we're going to need these functions, the coordinate transformations, to be differentiable in general. Okay, so this is the picture. And for example, you can see that the action for a relativistic particle, you'll remember from last week, we showed this action to be minus eta mu nu, dx mu dx nu, d lambda, d lambda, d lambda. Right, that was the action for a free particle, just the length of the world line. Now it's obvious what the action for a particle moving under gravity is. It's just minus g mu nu. The difference is that g mu nu depends on x, so it's a bit more complicated now. Oops. Okay, and that was Einstein's insight. If the action determining the motion of particles is just the length of their world line, then all I need to determine how particles fall in space and time, I need to know what is the length of the world line. And if I know the metric, then that determines the motion of particles. And his insight is that that will determine gravity. Now, so let me tell you a little bit about gravity. So gravity is going to be, is encoded in g mu nu of x. Okay? And immediately you get the idea that everything's going to fall the same under gravity because every object sees the same g mu nu of x. So that's how you'll explain that objects of the same, that all objects of any mass all fall in exactly the same way, because they're all falling in the same g. So it's universal. I.e., objects of any mass or composition, doesn't matter what you're made of. You can be made of copper or carbon or anything else you like, fall in the same way. Okay, so the intuition which led Einstein to this is very simple. So imagine I'm sitting here with a chalk, right? I'm going to fall. Okay, luckily not too far. And is the chalk going to fall with me? Okay, so I'm not very good at doing this, basically. Okay, you can imagine it, right? The chalk falls exactly as I do, right? So we both start out static. It doesn't leave my hand. I'm not really doing it well. But if you can try, I encourage you to do it from a bigger height. I'm not going to. Okay, the reason is that the chalk is falling with this action. It sees g mu nu. The mass is just overall factor. So the equations of motion of the chalk position are really just the same as mine. Here I put a bigger mass, but we're both seeing the same metric. That's the metric created by the Earth. And that's why we all fall the same way. Now, so let me show you this in a little bit more detail. So gravity is encoded in g mu nu of x. In fact, a uniform gravitational field a uniform one, by this I just mean that it's the same everywhere, is simply, maybe removed by a coordinate transformation. Okay, so you're familiar in classical mechanics with these fictitious forces, right? So if you sit on a roundabout and you try to hold yourself on, it feels like there's gravity, right? You're holding on. In fact, it's gravity pushing you outwards. But we know that that's just an artifact of the fact that you're sitting in a rotating coordinate system staying at the same radius. Okay, if somebody could describe you in a non-rotating coordinate system, then they would use the usual Newton's laws, and there's no funny forces. It's just that the object you're holding on to is actually accelerating you around in a circle. Right? That's one point of view. The other point of view is you go to the rotating coordinate system, and you say, oh, there's a fictitious force. Right? And it's the centripetal force. It's pushing you outwards. So you need some opposing force. So those fictitious forces are created by going to coordinate systems. In fact, to some different coordinate system. And that's what happens with gravity. Uniform gravitational field can be created or removed by a coordinate transformation. So let me show you that. It's kind of cute. Let's take a free particle. In Minkowski spacetime. Okay, so what does a free particle obey? Well, the equation of motion is just trivial. That's the motion of a free particle in Minkowski spacetime. And this is just telling you that it follows a straight line. The d2 dx squared is the acceleration of the line. But because the acceleration is 0, the general solution of this is that x mu is gamma v 0, 0 tau. Just linear in tau. In principle, I could add a constant here. I'm not going to, just to keep the math simple. So this particle is just following a straight line in Minkowski spacetime, right? Parametrized by this parameter tau. We're going to, the reason I write these two, so there are two constants here in principle, gamma and gamma v, but we're going to insist the particle is time-like, which means that eta mu nu dx mu d tau dx nu d tau equals -1. And this forces us to the equation gamma equals 1 over square root 1 minus v squared. The usual formula. Okay, so this particle moving in a straight line in Minkowski spacetime, with no forces acting, is a solution of that equation of motion. So let's take this particle and let's look at it in new coordinates. Okay, you see, if I did a Lorentz transformation, I do something a bit trivial. I just multiply the x by some constant, and all I'm going to do is change these constants. I multiply x by a constant matrix, the lambda mu nu. The lambda mu nu will act on this vector and just move around the coordinates, the components, and I just get some other constant vector times tau. So Lorentz transformations just change one straight line into another straight line. So if we're going to do something interesting, we need a coordinate transformation that is a bit more interesting than a Lorentz transformation. Let's first of all do it in general. X prime mu of x alpha. And so x prime is a function of x, and x is a function of x prime. Okay, sometimes I put the indices in the argument, sometimes not. You just, yeah, it's random. But this index in the argument is not a tensor index. Okay, it's just to indicate it's a function of those coordinates. So x is a function of x prime. And so d2x alpha d tau squared, what is that? Well, obviously, it is d by d tau of dx d tau. Dx d tau is dx dx prime times dx prime d tau. Just using the chain rule again. And now if I differentiate this, I get d2 x mu dx prime alpha dx prime nu dx prime alpha d tau dx prime nu d tau. Okay, plus the term where I differentiate the second piece. which is dx alpha dx prime nu times d2 x prime nu d tau squared. So 0 is this. So the particle was going a straight line in the x coordinates. In the x prime coordinates, it's not going in a straight line because you've got to cancel these two terms. The sum of them is 0. So that's saying the acceleration is something to do with the second derivative of the coordinate transformation, right? And so we can, since all of this equals 0, I can multiply by the inverse Jacobian matrix to put it over there. And then you can show that d2x prime nu d tau squared plus dx prime nu dx mu d2x mu dx prime alpha dx prime beta dx prime alpha d tau dx prime beta d tau equals 0. So in other words, the equation of motion of the particle in the new coordinate system involves a force. Suddenly I've just created a force, right, by a coordinate transformation. Just like the Coriolis force or the other fictitious forces, the centripetal force in classical mechanics. So this is the fictitious force. So that's in general. And what we're going to see is that when we study general relativity, indeed this will be the equation of motion of a particle in a general metric, g mu nu of x, will indeed look something like this. Okay, this is a very special sort of trivial case, but this trivial case is enough to reproduce a uniform gravitational field. So let's see how to do that. If I remind you, I'm going to take c equals 1 from now on in this course. Speed of light is 1. So let's take t prime to equal t. And so I'm going to write x mu as t x. So a coordinate transformation, let's consider the following one.
Back to what you wrote there, how do you go from alpha being a free index to mu being a free index in that first term?
Here?
So, yeah, right next to it. Yeah.
Sorry, this one?
So the first thing you wrote after the equality sign, on the right, just to the right of it.
Oh, this one?
There, yeah.
Oh, okay.
Now your mu is a free index, not alpha.
Yeah. Okay, so what I... Oh. Yes. So no, what I'm doing here is I've got to differentiate the d by d tau of this, right? So I differentiate this term. This I write as d by dx beta of x alpha dx prime nu, right? Times, so the derivative, sorry, d by d tau of this guy. I take this guy, I take its beta derivative and multiply with beta d tau. Right? That's the d by d tau of this guy. Is the d by dx of the same guy times dx beta d tau. Right? So maybe I've relabeled some indices. I'm not sure. Yeah. What? Yeah. Okay. That should have been an alpha. Thank you.
Then the other side.
Okay. And now is it at least right? It's yes.
Now it's fine.
Okay. Good. Yeah. Thanks.
Why are some of the terms partial derivatives and some full derivatives?
Because, okay, so just think about, basically because when you differentiate with respect to x's, it's always partial, because there are 4 of them. Partial derivative means d by dx alpha of, let's say, some function, some tensor function of x. What does that mean? It means it's equal to d by dx, the ordinary derivative of the function, but taken with the x x of mu not equal to alpha constant. Right? A partial derivative means you take the ordinary derivative with respect to one of the arguments, and you hold the other arguments fixed. Okay, so if I'm differentiating with the x's, I'm always taking partial derivatives, never total derivatives. Right? You need that instruction. D by dx with leaving t, y, and z fixed.
Why do you always do a full derivative with respect to tau?
Because there's only one of it. There's only one of it. So I've got some function here of x of tau, right? So this function depends on the 4 x's, and each x depends on tau. Right? So let's do this in some steps. So we'll have f beta of t, x, y, z. Right? So now if I do the partial derivative, dx, let me take one of them just to keep it simple. D by dx alpha, what does that mean? Well, it's got 4 indices. So it's a vector, it's a 4 vector, and the first component is df dt. And the second component is df dx, etc. Right? Now what I actually have here is something more complicated because each of these arguments depends on tau. Right? So if I want to calculate df d tau, what does that mean? It calculates, I've got to know about the tau dependence of all 4 indices. Right? So I write it as df dt. That's going to give me the dependence coming from here, dt d tau, plus df dx, dx d tau, plus, So if you really want to be sure you have this right, just write out all the terms. And at some point you'll get completely bored with that, and you will realize that this does all of it for you.
So basically you do the full derivative because you want to see how each of the components depend.
Exactly. Yeah. Each component is a function of tau. You need to differentiate with respect to each component and add them all up. That's what all this sort of notation does for you. Okay, any other questions?
How can we read that it's a uniform representative?
Say again? Oh, I'm going to show you. So I'm going to say, I want to allow more general coordinate transformations. These Lorentz guys, we're bored with them already. They're just constants, and it just takes me from a straight line in space-time to another straight line. So let's get a bent line. How do I make my curve, which was straight, how do I make it bent? Well, I do a coordinate transformation that's more general. Right? So obviously, so let's take x mu to be gamma v 0, 0 tau. That's the trajectory in the x coordinates. But in the x prime coordinates, it's going to be curved. It's not going to go linearly in tau. It's going to go like tau squared. Okay? So this will give us that t prime is gamma tau. I'm just taking this coordinate transformation and sticking in x mu is t and x. And x prime is gamma v tau plus 1/2 a gamma tau squared. And then y prime is 0 and z prime is 0. So in other words, the trajectory of the particle in the x coordinates was a straight line. The trajectory of the particle in the x prime coordinates is this curved line. Okay? And so just to interpret it, you can see this is vt prime. Naturally, it was moving with speed v in the original coordinates. And it's still moving at velocity t, but at least at t prime equals 0. But then it's going like this. So the particle in the primed coordinates is undergoing uniform acceleration. Okay, I should have said A is constant with A equals constant. All right, so just by a coordinate transformation, I've made my particle accelerate. In this coordinate system, it's accelerating. Okay, this looks like there's some force acting. So now you can check, you see, what we required when we solved the equation in the original coordinates, we required the particle has no acceleration and it's time-like. Okay, where tau was the proper time. When I go to these new coordinates, I still want the notion of a proper time. I still want something which is invariant under coordinate transformations to tell me how far along the particle's trajectory I am. And so I'm going to define tau in the same way as invariant. So of course we had eta mu nu dx tau. Yeah. We had this equals -1. This was true in the original coordinates. Let's now interpret this equation in the new coordinates. So how does it look? Well, the eta, well, it's just equal to this. All I need to do is express dx mu detour in terms of dx prime detour. So this is dx mu dx prime alpha dx nu dx prime beta dx prime alpha detour dx prime beta detour. Okay, so that is saying that in the new coordinate system, the quantity playing the role of eta is actually this. So this is G. This is G prime alpha beta of x prime. So in the new coordinate system, the particle is time-like, again, but it's not time-like measured with respect to eta. It's time-like measured with respect to this G. And so let's look at the G. What is the G? The G prime alpha beta of x prime, you can easily work it out. It's just given by these Jacobian derivatives, so you need to go and differentiate these guys, express x in terms of x prime, and differentiate. And what you get is -1 plus at prime squared. And then we have, so that's all in the 0, 0 component. And then in the 0, 1 component, you get minus at prime. And here you get minus at prime. This component you get 1 and 1 and 1. Okay, so that's the metric in the accelerating system of coordinates. And this metric is responsible for the fictitious force. Okay, so you see, by doing really something completely trivial, I just changed perspective, suddenly I seem to have gravity. And that's the situation with me and this piece of chalk falling. See, so this was Einstein's realization, that he realized, I can sit here on the Earth, and I feel this force of gravity, and everything feels the same force. Or I might be in a rocket ship, accelerating through space, right? Maybe this room is not on Earth. I don't know until I look out the window. Maybe I'm in a rocket ship in this room, and the rocket is accelerating. Okay, and I would feel exactly the same thing. And the reason is that this gravity is simply created by the change in perspective. Okay, so gravity can be created by going to an accelerated coordinate system. So in a sense, gravity doesn't exist at all. Okay, but that's not quite right, because it turns out that only a uniform gravitational field can be mimicked by a coordinate transformation. When I describe a non-uniform field, you see, for example, if I take into account that the Earth has a finite size, the particle trajectories actually converge towards each other. The force is not quite in the same direction. And the only way you can get that is actually by having the space be bent. You can't just make it with a coordinate transformation. And actually, we're going to show that in a second. So, but it's very important that when you go to these funny coordinate systems, which are not given by Lorentz transformations, you no longer use eta mu nu to measure space-time geometry. You use this guy, which is the transformed eta mu nu. That's, you know, if this is not Poincare transformation, then if x of x prime or x prime of x are Lorentz transformations, this is eta. But if they're not, if they're more general, then it's some matrix. And so this metric corresponds to uniform gravitational fields.
Sorry, how did you get this metric?
I just calculated it. Okay, so I can do that. So what I have to do is work out x as a function of x prime. Right? That's what the matrix is defined at. Okay, that's what it's defined. So I've got to contract all these indices. So let me calculate it for you. You see, this is x prime as a function of x. I need x as a function of x prime. So that's easy, because I've got t equals t prime. That's just inverting. But here I've got x is equal to x prime. I pull this over to that side, and then notice that t is t prime. So minus 1/2 a t prime squared. Okay, that's the inverse coordinate transformation. Now, how do I calculate this? Well, let's do the 0, 0 component. I get, this is minus 1 in the 0, 0 component. So I'm going to get dt dt prime. If these two are 0, this is t. So I get dt t prime squared, right? So the first piece of this is minus 1. That's the minus 1 coming from these two indices both being 0. But notice that if these two are both 0, so I'm up here, I still get something because dx dt prime is not 0. Okay, so let me write this down. The 0, 0 component, right, what is that equal to? Well, it's minus dx0 dx 0 prime, dx0 dx0 prime, x0 prime. And then I get the same thing, but where these indices, these two can be 0, or they can be 1, plus dx1 dx0 prime, dx1 dx0 prime. Right? So this term is just minus 1, because both of these are 1. Dx prime, dx prime, this is dx1, dx0 prime, is dx dt prime, is at prime. And so this is at prime squared, etc. Okay, so literally just calculate. And you'll get these terms basically again because the dx dt prime you get coming with dx dx prime. Okay? Yeah.
In the coordinate transformation over there,
yes.
Shouldn't we put y prime equals y and c?
Yeah, I didn't bother. I didn't bother. These guys are 0. So it's not going to change the trajectory. I put it here. But yeah, you're welcome to write that down too. Y prime equals y, z prime equals z. Any other questions? Now, it's obvious, you see, it's obvious from this point of view that if a uniform gravitational field is just a change of coordinates, then of course every particle is going to see the same acceleration because they all see the same change of coordinates, right? I mean, all I did is change coordinates. Everybody's measured in the same coordinates, so they all have to respond in exactly the same way, obviously. And so that was Einstein's insight. That's why everything falls in the same rate, because you can remove the force with a change of coordinates for everybody. Now, there's a big difference between this picture and special relativity, which is the following. Note that unlike eta alpha beta, g alpha beta of x, well, I've derived g alpha beta of, or g prime, is not invariant under coordinate transformations. So the whole point in GR is to say we're going to describe spacetime with a quantity which is a tensor and changes under changes of coordinate transformation. In special relativity, we have this eta, which is an invariant tensor. It does not change. It's the same in all coordinates. Okay, so that's very different. And what it means is we need some principle to determine what is this G. You know, we've got a 4x4 matrix function of things, and we don't know how to determine it. Could be anything. Okay, so what I hope we'll do this week is find the equation that determines this. And that's the Einstein equation. Oops. So that's what makes Einstein's theory so much more ambitious than Maxwell's. You see, Maxwell just assumed the arena is fixed, and you stick in this eta. Eta is just God-given quantity. It's the same for in all coordinate systems. In Einstein, you instead introduce a G, and you don't know what it is. But the universe, the equations governing the universe determine what the space-time is. So space-time becomes determined by the laws of physics. Okay, it's 10:15, so I think you ought to break now. And what we'll do next time is we'll try to sort of go backwards. You see here, we took an eta, flat space-time, and we looked at it in a silly coordinate system, or some coordinate system, where it looked like there was gravity. But we could just stick to the original coordinates, and there would be no gravity. Let's now take the reverse point of view. If I give you some G, somebody gives you a G, right? What are the laws of physics given a G? And in particular, how close are those laws to the laws where G is eta? Can you think of G as being approximately eta in any way? And the answer is you can, and it's very beautiful, okay, in the following sense. So imagine a curved geometry, okay, some curved space, like the surface of a ball, or even more general, something lumpy. And so here's your geometry, or space-time. And then the point is that if you go near some point on that geometry, providing it's fairly smooth, if you go really near to some point, it's going to look flat. Right? So every geometry, every sufficiently smooth geometry is locally flat. Okay, it just means that I can always go up to some point and just look in its immediate vicinity and it basically will look flat. All right? And it turns out in this vicinity, the laws of special relativity hold. So this method of constructing the laws of physics by putting in a G always reduces to special relativity in the neighborhood of any space-time point. So for short times, short distances, you recover special relativity just because geometrically any curved space is locally flat. In fact, that's one of the hypotheses of Riemannian geometry invented by Riemann in 1820 or 1830s, is that whatever curved space you think about, it should be locally flat. And so this local flatness explains why special relativity is so good. Because most of the time we don't care about the expansion of the universe or the gravity. You know, we can work as if we're in some local region of space-time. In any local region, you can always choose coordinates in which g mu nu is eta mu nu. And so we'll prove that next time. And so what it says, so Einstein proposed what he called the equivalence principle, which is basically you take the laws of physics without gravity, where you have an eta, and you simply promote eta to g. Everywhere that eta appears in your equations, you put a g instead. Okay, and in that case, you guaranteed that those laws are going to hold in small regions, the original laws you discovered, and so you don't change the laws of physics for special relativity. You simply accept, you only change the laws of special relativity on larger scales. You don't change them on short scales. It's an extremely conservative theory. Left all of Maxwell alone, all the other laws of physics alone, and just said, space-time is a little bit bent. And if I go to sufficiently large scales, I'm going to see that bending. And that's gravity. Okay, so definitely the most beautiful idea there ever was in physics. Okay, so we'll see next time that if I have a general G, nevertheless, around any particular point, I can replace G with eta in the small neighborhood of any point.